afternoon. Thank you all for coming today to our fourth colloquium this year. And we welcome Dr. Heather Johnson from the University of Colorado in Denver. She's an assistant professor of mathematics education. She got her PhD from Penn State University. Before that, she got her master's at Penn State University. Before that, she got her bachelor's at Penn State University. So I don't know what that's referred to. I assumed it was a triple Penn Statian, but I'm not sure if there's a, I'm just going to go with that. But before that, before getting her doctorate, she taught for approximately 15 years at Central York High School in York, Pennsylvania. Since getting her doctorate, she's been a Star Fellow and published various articles in the Journal of Mathematics Behavior, Mathematics Teacher for the learning of mathematics as well as others. She received the Lincoln Research and Practice Outstanding Publication Award from the Mathematics Teacher for her article in 2014, Reasoning About Quantities That Change Together. So we welcome Dr. Heather Johnson.
So thank you for having me, and being a triple Penn Statian, I kind of like that. I like that idea. You know, so I started off as an undergrad, and then I escaped Central Pennsylvania. So Penn State's right in the middle of the center of the state, and so I taught in the South Central portion and got my master's degree at another campus of Penn State, and then had been doing some work with teachers in the state, and folks from Penn State who I had known in undergrad said, you know, why don't you think about coming back and getting a PhD? And I really think I was concerned that they might stop asking, and the sheer fear that I might not actually be able to start doing those kinds of things brought me to that. So I really thank you for having me, and I look forward to the opportunity to engage us in thinking about how we can lay groundwork for function and rate by leveraging a dynamic computer environment to foster students' quantitative and variational reasoning. And before I get started, I'd like to thank others who participated with me in this research. One, Evan McClintock, who's here today, and also two graduate students who participated in some preliminary analysis and data collection with me, Richard Lambert and Jennifer Ahmed. And so I've planned this talk to be about 40 minutes, and so I look forward to having a lively discussion afterwards. And so hopefully we can hold questions until the end, and I'll share with you some things that have been going on. So just to get started, I'd like to lay out some things that I think we can all agree on. And first of all, I want to let you know that there are more words on this slide than any other slide that follows. So I've been working with, my daughter designed a yearbook, and they were doing a lot of photo where they laid the pictures along the yearbook and overlaid things on top of that. So I was thinking about that when I was designing this talk. But so laying out some things that I think we can agree with. One, that middle and high school students need opportunities to engage in powerful reasoning about important mathematics. And two, that we really need to know more about how students develop conceptions of these things that we call function and rate. And so in order to do it, I'm arguing that if we study how students form and interpret relationships between quantities that can change, it can really provide a fertile ground for this endeavor. And so to illustrate, I'd really like us to consider a triangle that's filling with area. And in doing this, students can think about different relationships that are involved in this animation when they're making predictions about the situation. And throughout this talk, I'll be using the word envision a fair bit, and by that I mean not imagining just what might happen, like a moving triangle, but actually thinking about changing attributes. And so, for example, a student might envision a relationship between the changing side, AD, and the area of ABCD, such that the change in area depends unambiguously on the change in the side length of AD. And we might call that, say that the area of ABCD is a function of AD. Or another student might be thinking about how the area of ABCD is changing as the length of AD increases. And so we might be able to talk about the area of ABCD increasing more slowly as AD is increasing, or talking about the rate of change of ABCD as increasing at a decreasing rate with respect to the increasing length of AD. And so my intent with these examples is just to provide some illustration as to how thinking about forming and interpreting these relationships between changing quantities can inform our thinking related to function and rate. And so, over 20 years ago, and really it's been that long, and I don't want to know what grade some of you might have been in at that time, we've developed some dynamic environments to provide students opportunities to reason about the mathematics of change and variation. And Caput argued that these kinds of opportunities could democratize students' access to calculus, which is still a gatekeeper course for many STEM careers. And we know that these dynamic computer environments, I have an example from SimCalc here, that involve linking dynamic animations and graphs, they can provide students with opportunities to think about change and variation. Yet, students interacting with such environments might be paying a lot more attention to particular amounts of change or amounts of quantity than actually envisioning change in progress or engaging in variational reasoning. And so I agree that it's useful for students to interact with these dynamic computer environments. I mean, I design them. And so, like any promising educational tool, it's not the tool that does the work on its own, but rather we, as teacher researchers, need to have a goal beyond just engaging students in interacting with an interesting environment. And so what I'm suggesting today is to engineer tasks that can incorporate these kinds of environments in ways that provide students opportunities to engage in variational reasoning. And so when I think about these opportunities to engage in quantitative and variational reasoning, I want to just talk a little bit about what I mean by some of these things, just to give some background. And so when a student's engaging in quantitative reasoning, she's reasoning about an attribute of an object that she can imagine as being measurable. And so we could think of a student who could conceive of area as a measure of an amount of flat space that I could cover. And so importantly, I distinguish measurable attributes from other kinds of attributes, like physical or numerical attributes, that students may or may not conceive of as being measurable. So for example, a student looking at a triangle might think about pointiness as an attribute. Now, while I might be able to think about pointiness as something that I could measure, that student might be thinking about pointiness as just a physical attribute of the triangle, something that they can see. In another case, a student might be determining calculations to find amounts of area. So, for example, I could take 1/2 times 5 times 10 and get 25, and yet not really be thinking about 25 as representing a number of units that could measure the area of a triangle. And so when I talk about these objects of reasoning, including physical or numerical attributes, just importantly, I'm talking about them from the student's perspective. So it's the students envisioning what might be measurable or what maybe a physical or numerical attribute in terms of engaging in these things. And using words for this, when I talk about students attending to physical or numerical attributes, I'm using the phrase pre-quantitative variational reasoning. And so to distinguish between variational and covariational reasoning, I'm using variational reasoning to mean a single quantity that's in the process of changing, whereas covariational reasoning would involve forming and interpreting relationships between quantities that can change. And so with either form, the object of the reasoning can vary. And I'm distinguishing between students who are engaging in variational reasoning such that the object of the reasoning is a measurable attribute, quantitative variational reasoning, or variational reasoning such that the object of the reasoning is a numerical or physical attribute, pre-quantitative variational reasoning. And so, given the centrality of graphs to the dynamic computer environments I'm dealing with, I just want to say a couple words about what we know about how students interpret graphs. And we know that students can make sense of graphs as pictures and interpret them iconically, to think of them as a picture of the situation. And recently, Moore and Thompson, I think, provided us some really useful ways of thinking about graphs through the constructs of static and emergent shape thinking. So, such that static shape thinking, a student would envision a graph as a manipulable shape. So like this graph here, well, it looks like a hook. And that's not to say that it's representing a triangle, but rather it's a shape that I can envision that's representing the situation. In contrast, a student could envision this graph as a trace of a relationship between covariant quantities. And so important is that Moore and Thompson claim that if you have, or you're thinking about this graph as representing a trace of a relationship between these quantities, that student would be engaging in covariational reasoning. So a student who's interpreting this trace as a relationship is also engaging in covariational reasoning when interpreting these graphs. So given this background, I'd like to raise some questions. One, how could we use tasks to leverage a dynamic computer environment to foster students' variational reasoning? And two, in what sorts of variational reasoning do students engage when interacting with these tasks? And so I'll start with the first question, thinking about tasks that leverage this environment and how we might engineer opportunities for students to engage in these kinds of reasonings. So for the purpose of this talk, I'll be talking about and focusing on this filling triangle environment that I developed with Geometer's Sketchpad software. And it links a right triangle filling with area with a dynamic graph, and also has some opportunities for students to be able to hide or show different features and to change the way the animation progresses. And so a task that I implemented with students with this particular environment involved two key activities: prediction and interpretation. And so after viewing the triangle animation and talking with me a little bit about how does the area change as the height of the triangle increases, students had opportunities to make predictions about a graph relating the area of ABCD and the length of AD prior to seeing any of the linked graphs on the computer. And after making predictions, then seeing the linked graph, they had the opportunity to make interpretations about what they saw. Important, the task problematized the use of a formula to calculate amounts of area. And when I say problematized the use of the formula, I mean it in the sense that I made it problematic for the formula to be able to be having numbers that could be used to then reason about variation from those numbers. So instead, I generated opportunities where students could engage in amounts in the process of changing, as opposed to working from particular number to number to number to number. And so let me tell you a little bit about what we did. I led a sequence of 3 days of whole class instruction with 4 sections of a 7th grade pre-algebra course. And after the instruction, I conducted a total of 7 clinical interviews with pairs of students. And so 14 students in all participated in both the whole class instruction and the follow-up interview. And Evan served a supporting role during the lessons and the interviews. at times interjecting prompts to provide further opportunities for students to explain their reasoning or to gather evidence of students' variational reasoning. And so you'll hear one of his questions a little later in the talk. And because we intended to provide opportunities for students to engage in variational reasoning, not to conduct a teaching experiment in which we would develop the variational reasoning, we selected students purposely for the interviews who demonstrated variational reasoning in the whole class instruction. And so during the whole class instruction, students had the opportunity to interact with the filling rectangle environment that you see here, and then during the follow-up interview, we presented them with the filling triangle environment. And so I also really want to contextualize this a bit for you and tell you about the richness of the setting and where we worked. So we conducted this study at a public charter middle school to which students applied to attend. And so even though the school had a rather rigid curriculum, scripted lessons, they allowed us to come in and do this replacement unit instead of the review that students would have gotten instead, which I'm sure you can imagine what that review might have been like. So it's really wonderful that we got to help them to engage in something else. And the school is interesting because it's located in a gentrifying part of the city. And so the students who attend the school don't necessarily live right where the school is. And 92% of the students who attend here are eligible for free and reduced lunch, and 94% of the students identify as not being white. And I just want to recognize that we carry the weight and responsibility of us being privileged white researchers who go to a school and work with students who aren't identifying as white. And I want to talk a little bit about, prior to working on this research, I spent time in the students' classroom, not to pre-assess them or engage in early research interventions, but rather to help them to recognize that I was an adult who actually was going to be there for more than just a day or two, and to develop a rapport so that students might feel like they could actually be able to answer questions and to engage with me, both when I would lead the whole class instruction and also when I would lead the interviews. And in sharing with this with you, I asked us to think about, back on Gutierrez's call, to conduct research that doesn't focus on gaps between students from different socioeconomic statuses or students from different races, but rather to investigate complexities within a group of students. And as I intend to demonstrate, these students with whom we worked are really most worthy of our attention. And so we sought to investigate students' variational reasoning. And by interviewing students in pairs, we really thought that they'd be a little bit more comfortable talking with us because they'd already be with someone with whom they were also comfortable. And to just tell you a little bit about the data analysis, we did multiple passes. We started by coding for variational reasoning when students were engaging in something that was in the process of changing. But quickly,
But when you 21, it takes a long time when we get to ball right here. It goes to 1 to 10 real fast, and then once it gets to the 20, 21, it starts taking, and it goes more slowly.
but so we really found out that just coding for variational reasoning wasn't doing the kind of work that we wanted it to do. And that's when we looked at the objects of students' reasoning. And so in this case, we coded the students' reasoning as variational, focusing on a numerical attribute because of the object of the focus of the students' reasoning. And so I can contrast this with other students who were reasoning about who had different objects of variational reasoning. So in the case of Blanca,
It's not a triangle the whole time. Because like the rectangle is rectangle the whole time. But this is a chapter thing, and then it eventually goes into being a triangle. So it would be a different story if it was 10.
so it's a trapezoid that eventually goes into being a triangle, which would be a different story if it was a triangle the whole time, like the rectangle that was a rectangle the whole time. And I provide this as evidence of a student engaging in envisioning something in the process of changing that from our perspective was a physical rather than a measurable attribute. It was a shape that was in the process of changing. And so we can distinguish this from a student envisioning a measurable attribute in the process of changing. It's in the case of Myra.
Can you say how does it increase? Like, it's getting smaller and smaller every time.
So when you say it's getting smaller and smaller every time, you mean
The area.
the area's getting smaller?
Because the area is getting bigger. Yes, the area is getting bigger, but how much it increases is getting smaller.
And so, just giving you an idea of the scope of some of the different kinds of reasoning. But yet, even though the coding of the different forms of reasoning was useful, we found that isolating just the different types also didn't really provide us a sense of what the students were doing, because often they did more than one. And so I'll just show you a little excerpt here.
Because it's all about A and B.
Okay.
A and B, the base.
The base of A and B.
Mm-hmm.
Then the area will be way different, but the same structure will be the same structure going that way.
So he's tracing along the graph that he's seen that the structure will be the same. And so, in terms of thinking about how we made sense of this, so once we realized that students didn't just engage in one or the other exclusively, but rather mix these kinds of things, we then started to look at what was the kind of prompt that we were asking them. And what we really determined was that prediction and interpretation matter. And particularly, prediction told us a lot. So I'm going to go back and just play a short clip of Tomas, who we heard about in the numeric. He was talking about the numbers just a couple of minutes ago. I had asked him to predict a graph for the triangle, what it would be like. And you might notice students playing around with little bendable wax sticks. I had given them some wax sticks to try to provide them opportunities to think about changes continuing. And so this graph that you see up to the side, he had pressed a wax stick onto the paper, then traced it, and then peeled it off. And so that's what you see.
So can you tell me what slower means? What going slower means in terms of area and silo?
And this picture is the same as what's on the screen.
So this is the bottom, is an open space, and the white gonna concentrate, but as the length of AB and BC in the top, the area it has less room, it increases by much less than the bottom. It goes a little bit slow. So the area goes slower, and then it goes back down to the constant rate again.
So this constant rate up here is when you come back down and graph the down part again?
So to give you a little bit of a sense, coded for variational reasoning, looked across the different types, how students might engage in those types at the same time. Paid attention to the prompt that we were asking. Was it a prediction? Was it an interpretation? And so just to kind of step back a little bit and give you an idea holistically, all of these students engaged in variational reasoning with the filling triangle environment during the whole class instruction. That's why we picked them. 9 of the 14 students engaged in variational reasoning when working with the filling triangle environment. And I'd like to tell you a little bit about what the students taught us and a little bit of explaining of why that's the case. So when students were attempting to make calculations, they weren't demonstrating evidence of engaging in variational reasoning. And so prior to Myra's exclamation,
Oh, I get you now.
she'd been trying to determine amounts of area, and she was very persistent with trying to think about how on earth she would figure out the area of this trapezoid, and she couldn't remember the formula, and she wasn't sure, and she wasn't getting numbers that she liked, and they weren't helping her. And so I suggested that she not focus on particular amounts of calculations. And in Myra's case, it provided her with an opportunity to engage in variational reasoning, yet that prompt wasn't necessarily perturbing for all of the students who were engaging in calculations. Of the 5 students who never demonstrated evidence of variational reasoning during this interview, all 5 of them remained focused on making calculations and determining amounts of area in the filling triangle. And one of the things that we were thinking about when the students were working with the filling rectangle in class, we think that they were able to draw on some of the calculations that they had actually made and then talk about what happened, as opposed to actually drawing on envisioning these quantities in changing. But when the triangle came around and they couldn't actually get those numbers to work from, it really changed how things were working for those students. And so another thing that was really useful for us to think about was that this pre-quantitative and quantitative variational reasoning aren't things that are mutually exclusive. Like when we went in, we were really thinking that, okay, we're going to have some students who are working with the physical attributes, maybe some who are more focused on the numbers, maybe some who are paying attention to quantities. And while a few of the students did tend to engage in just one form of the reasoning, most typical was for students to engage in a variety of forms in conjunction. And more importantly, when students only engaged in pre-quantitative variational reasoning, so even if they were envisioning these quantities as, envisioning attributes as being in the process of changing, if they weren't also envisioning measurable attributes being changing, it really limited the scope of their reasoning. So, for example, when the object of a student's reasoning is a physical attribute, so you may remember Blanca who talked about the trapezoid and it's not a triangle the whole time, it really afforded little more than matching a graph to a shape.
We had anchors, like for rectangle, it was more over than up.
Oh,
So that's like the same thing with this. Like ignore the fact that it's a triangle.
Okay.
Look at this side, see how it's thicker?
uh-huh.
So if it was thinner, then it would be more up than over.
Okay.
If it's thicker, it would make it thinner.
And so if you think about it, now the graph that I had given the students had the length of the height of the triangle represented on the base. And so it, in fact, her claim that, if the base is longer, the graph is going to be more over than up. It's not even really actually consistent with what the graph would be, but importantly, more important than whether or not it's a correct claim, is what she's using as evidence to base the claim that there's an attribute. If the attribute is like this, then the graph is going to be like this. So rectangles make lines, triangles make hooks or curves or things like so. It's this idea that if students remained focused on physical or numerical attributes, it really limited beyond just making these matching kind of distinctions what they were actually able to do. And although having a physical attribute as an object of reasoning is limited, it's not necessarily entirely unproductive. And I want to go back to Sergio, whose clip I played at the beginning when he was talking about it all being about A and B, and telling us that if we change A and B, the area will be way different, but the graph will stay the same, it'll be the same. But what's interesting is when I started to, you'll hear that again, but then I also started to go back to ask him, so can you tell me about that? Can you use the area and the length of the side to tell me about this? And you'll get a chance to hear a little bit about what he says.
Because it's all about A and B.
Okay.
If you change the length of A and B,
Mm-hmm.
then the area will be way different, but the same structure will be the same structure points at length.
Can you use the area of the triangle to explain why? I think that's a really, really amazing observation that you're making. But can you use can you tell me about the area to explain why you were talking about that?
Because all triangles are close in,
Okay.
have three sizes that shows like an expanded one, like in a square. So when you go up more on the triangle, and the area kind of decreases because not that much space can be inside it.
And so this was something interesting that we found where students would leap in terms of thinking about having an insight. So as I change this length of A and B, I can make this prediction about a structure of this set of graphs. But yet also thinking about being able to explain that drawing on quantities, you'll notice that he went to, oh, well, the triangles point in, they're closed in. And so we saw with students as they were beginning to emerge in some of these ideas of thinking about the quantities, that we would also see this mixing of them paying attention to these physical attributes as they were working with this situation. So of the 14 students, 4 of them predicted that a graph relating the area of the triangle, the area of ABCD and the length of AD would be nonlinear. And all 4 of those students who made that prediction were engaging in quantitative variational reasoning. So we had 14 variational reasoners, 9 in the rectangle environment, 9 then reasoned variationally when working with a triangle, and then 4 of those 9 who were engaging in quantitative variation, 4 of those 9 predict the nonlinear graph. All of the students who predicted the nonlinear graph were engaging in quantitative variational reasoning, yet there were some quantitative students who demonstrated aspects of quantitative variational reasoning that didn't also predict the nonlinear graph, and I'll talk a little bit about why that is. But as I've said before, that prediction really matters, and an important thing that we learned about prediction was that students weren't always representing the quantities. The quantities that we had provided for students on the graph weren't necessarily the quantities that the students were representing as they were engaging in when they were working with this task. And so I'm going to go back to Tomas, and I'm going to pick up a little bit before the clip that you saw at the beginning, and then also give you a little bit more of the scope. And what I want you to think about is what he's trying to represent as he's talking about what he actually produced. So we'll see him describing what he actually produced.
So first, like I said, we're going to concentrate, and then go slower. So it's not going to steep, and then the other side. That's like curve a little bit to the right, and then go to the concentrate again. So it's near the top. Because at the bottom it goes to concentrate, and then at the top it goes kind of slow.
And when you say it goes slower, can you talk about like how, when it goes slower, are you talking about the area of ABCD?
Yeah.
So can you tell me what slower means, what going slower means in terms of area and side length?
So this is the bottom, this is the bottom open space, and it's white, gonna concentrate, but as the length of AB and BC is in the top, the area, like, it has less room, it increases by much less than the bottom. It goes a little bit slow. So the area goes slower, and then it goes like down. We're gonna concentrate again.
So this constant rate up here is when you come back down and grab the down part again?
So if you remember, when he first pressed the animation back at the beginning when Tomas was talking about how the numbers were changing, the triangle was partially filled with area. And so the triangle filled with area and then came back down and refilled. And so when he sketched this graph, he was sketching his perceived speed at which, the speed that he perceived at which the area of ABCD was to be changing as the animation progressed. So thinking about the triangle filled with area pretty quickly, then as it got to the top of the triangle, it went a little bit more slowly, and then when it came down to the bottom, it filled again. And you'll notice that he didn't have a problem extending the graph in terms of continuing as the length of AD was not something he was attempting to represent. And I don't take a whole lot of stock when I asked him, is the thing you're representing the area? And he says, yeah. I don't take a lot of like, oh yes, he's representing area. But what I do pay attention to is his purposefulness, and look at this amount of space down here. Here's what I'm trying to do with the triangle, and here's how I'm connecting it to the graph. And then this is what's happening. But you'll also notice he goes from talking about quantities to then talking about the triangle being closed in, and then talking about the change continuing. And with this, we found that in investigating the students' reasoning, when students were beginning to use some of these quantitative forms of reasoning, we saw emergence of those, and then we also saw students work with other forms of reasoning as well. And so to kind of give us some things to think about, if students are only attending to physical or numerical attributes of the objects, it's limiting their reasoning power, even if they're engaging in envisioning things to be in the process of changing. So this is to say that envisioning attributes in the process of changing is good, but it's not enough. The attributes that students are envisioning, they need to be conceiving of those as measurable from their perspective. And so if all they had to work with were the physical attributes, we got a lot of the matching. Triangles look like this, rectangles look like that. Also, when students were focusing on making numerical calculations, they weren't engaging in variational reasoning, and particularly we noticed this with the filling triangle environment. So
If we don't worry so much about how you actually find the area, if you just think about, and so if we just think about how does this area change? How does it increase as AD gets bigger? What do you increase by?
Oh, I get you now.
I really do like that middle school students they wear a lot on their sleeves, so when they get excited that something's different. And Myra's was both exciting and also really gave us a lens in terms of thinking about the object of students' focus. So when she was, even though in this instance she shifted to focusing on measurable attributes, she remained focused on numerical attributes throughout the remainder of the interview. So she wasn't one of the students who was predicting a relationship between the area and the side length that wouldn't be linear. She was back to thinking about, oh, well, the rectangles look like this, and so it'll probably be about the same. And so when we think about this idea of pre-quantitative and quantitative variational reasoning, focusing on physical attributes isn't entirely unproductive. And it also really gave us insight into a way of thinking about static shape thinking that has a quantitative aspect to it. And so if we go back to Sergio's thinking about this graph, it was all about A and B. As the length of AB changed, the area would be different, but the structure would be the same. So he was thinking about this as a thing that he could take as a manipulable shape, but yet it was still connected to quantitative aspects that he could conceive of as being measurable. And in addition, this dynamic computer environment also afforded us to be able to think about what was happening with these thinking about shapes in ways that it's not necessarily separate from quantitative. And it really also helped us to push back on some of the literature. If you remember some of the literature done out of SimCalc, so back in 2005 or 2002, Stroop claimed that you really need to have kids work with varying rate before constant rate. And something that we found from this environment is that I suggest that what we've done has provided some evidence to refute that claim, that it's not about the kind of change that students get, so it's not about getting what we perceive to be varying rate before constant, or vice versa, but it's about problematizing the calculations, that if we can help students to not be focused on resulting amounts and then using those amounts to work from something, but rather engage students in envisioning these attributes as changing, ideally measurable, but working to that, we can actually really make progress in terms of students' variational reasoning. And so, something important to notice that I really want to bring out is we gave students prompts that at first were intended to engender covariational reasoning. I mean, we asked students things like, how does the area change as the length of AD increases? And what we got weren't covariational responses. As students, what I'm not claiming, there were some instances during the triangle when students were engaging in, there were some times of maybe very small forms, but what we saw was that students were predominantly engaging in variational reasoning. And what I want to say about this is we're not claiming that the students' reasoning was lacking. We're claiming that the kinds of reasoning in which the students were engaging, we ought to be paying attention to as a way to help students to begin to engage in covariational reasoning. That what we saw, quantitative variational reasoning in particular, is a route for covariational reasoning. Now, this isn't to say that it's an end goal. I'm not suggesting that, oh, we want to get students reasoning variationally and that's it, but rather that we want to think about this as a place to start from which more powerful reasoning could then emerge. And so, just to conclude, I'd just like to provide us some things to think about. And so the research that I presented with you today has some implications for task design that could engender opportunities for students to engage in covariational reasoning. And in particular, we're arguing that incorporating both situations that involve, from our perspective, constant and varying rates of change, and problematizing students' calculation making can be ways in which we can engender this kind of reasoning. And also, if we really want to foster their reasoning, we ought to be having students engage in making predictions as well as interpretations. So it's not just about showing students an animation and having them look at the animation and see what happens, but rather predicting what happens before they actually see the motion, and then engaging in interpretation and making sense of that after that particular happens. And so if we think about this, if students in middle grades were able to develop ways of envisioning attributes as continually changing, and then be able to use these things we call variables to represent that change, we could really have students be set up in a way that could enable them to think about variable as actually something that could vary, as opposed to a placeholder for a number, which we really see so much more prevalent in our students with whom we work. So, questions?
I have a question about the groups, because you had the 14 and you had them in pairs.
Yes.
Did the results, within a pair, did you tend to get the same result, or did you get much variation between the two students in the group?
Yes. So, so that is to say that we had pairs that students were very similar, and we also had pairs where students were talking about different things. So if you take Blanca and Krista in the corner, Blanca was focusing on, she was engaging in variational reasoning, focusing on physical attributes. Krista was making calculations. I mean, I don't know if you noticed, she was twirling the wax stick around her pencil while Blanca was talking about how the physical attribute was changing. And it really said a lot to me. Like, that was also something that I noticed when the students were talking past each other. When one student would be talking about something that really was not an object of the other student's reasoning, I would notice lots of playing with whatever was around on the desk. But if we take that to Jorge and Tane, they were both engaging in variational reasoning that was focused both on numerical and quantitative aspects. And one of the things that I found is, as they were working, Tane was so delighted with herself at this point because she had predicted that the graph was going to be piecewise linear. She said it's gonna go up until it gets to a certain point, and then at that certain point that was yet to be named, it would start to go in a different way. And so she was going, and then it was gonna go, and she was like, yes. They were laughing to themselves. Navarro and Daria were both very focused on calculations. And it was really interesting because Navarro was all over the variational reasoning during the whole class instruction. And then when he was working with the filling rectangle, and what we learned was that he was focused on, I get this much amount of area, he got the amounts of area, and then he thought about how the amounts of area changed, and when we problematized him being able to just get these particular amounts that he could then work from and think and run through in that way, it became much different. But this was his prediction for how the graph was going to go for the triangle. He's like, I think it's going to be about like this. And then Tomas and Simon went back and forth a little bit. Tomas knew a lot of the words. He told me, Simon on the left here knew a lot of the words. He told me a lot, like, it's a constant rate. He would put out all of these words that he thought it would be very impressed with if he said. So then if I didn't like get all excited when he said a fancy word, then he would just sort of fall back a little bit. They were very focused on how the numbers were changing, but then also began thinking about how how the relationships were changing. But when these two drew the graphs, really different. So even though I gave them the the wax stick, Simon's like, okay, can you give me an amount? Like, can I say the base is 2? And then can I just work with it? And so he was using an area formula for a triangle to determine amounts of area and putting his wiki stick down like, okay, here's a point, and then he just press it to the next point and press it to the next point and press it to the next point. Tomas was doing, they were working completely separately. He was doing something entirely different. Before the graph that he presented that I showed you, he actually drew first. He drew which just looked like this. So he told me, oh, it goes up, and then it kind of ends up finishing. And then he went, but he's like, no, that's not what it does. And then he went and continued and went further. And so just to give you a little bit of an example with each of those, what we noticed were that pairing students who were closer together in terms of reasoning, we had tried to nail it based on what they had worked with in class, like trying to get students that were close enough. So thinking theoretically, we blended theoretical paradigms when we worked with these students. So we were analyzing through a cognitive lens, really looking for students' reasoning, focusing on students' reasoning. But when we designed the tasks and we designed the setups of the environment, we drew on sociocultural theory in terms of thinking about it. So we thought about the zone of proximal development and tried to get students who we thought would be engaging in similar types of reasoning so that we would be able to have situations in where we might be able to engender these kinds of conversations, because we were trying to optimize our ability to investigate this object that we were studying, which was the reasoning. And so what we found is that, in the pairs, that was how some of the work was done. So it was a long answer. Yes?
Have you thought about, when you're working with these students, the distinguishing between, say, a planar region, okay, so you just got some region out there in the plane, and that group that you might want to call the area of that region, okay, so somehow there's a big distinction in my mind about taking that planar region and somehow thinking about its area, which is quite different than just talking about the planar region.
Mm-hmm.
So what constitutes, have you thought about what you would attribute to the student that would say, okay, I'm thinking about this area rather than just the region? I mean, how can you make a distinction between students who do that?
Yes, we think that we can. And ways in which that we've done it. So in some of the whole class instruction, I went about trying to investigate what students, what they were thinking about when they used the word area. Because I think just in terms of saying area or looking at a shape of a region, I like to assume that students are thinking in the least sophisticated possible way that they could be thinking about a situation, and then if I want to apply to say that they're actually reasoning about something measurable, I want evidence for that. And so if I go back to Tomas, who was going between the graph and between the triangle, one of the things when he was talking about the different amounts of space being covered, so I would say that I don't know exactly that he had a particular unit in mind with which to measure that space. So how was he thinking about quantifying that area? In that moment, I'm not exactly sure. But I take that as a really different thing than Blanca, who was saying, well, it's a trapezoid most of the time, and then it turns into a triangle. And one of the ways that I think about it, I guess I go back to, I think about the Van Healy levels as well. I think about properties of objects versus objects as just things as just looking at a triangle that's just a triangle versus envisioning a triangle that's an object that has properties. And so a lot of the questions that I asked when I asked Sergio, who's not up here, but could you use area and side length? Because I told him, I was like, that's a great response, but could you use area and side length to tell me more about that? I wanted to be able to analyze whether or not they were able to use those properties of objects. And so when I was talking about measurability, I'm not claiming that they yet envision a unit with which they could use to measure, so quantification. But I'm claiming that they could conceive of this thing as being measurable based on attending to these constituent properties. So that's how I was thinking about it. Yes?
Did you see at any time where the dynamicism of the program actually caused them to add the all-important time variable? Because I saw a couple times you used to talk about going slower and faster, so did you see that a lot? Or?
So I really like that you brought up this time variable, because something that we've really thought about a lot is in terms of thinking about what constitutes covariation. Because I mean, one way that I could have talked about Tomas's work was that he was talking about this area varying with respect to time. But I don't think that he was actually talking about, and I don't think he was conceiving of two things as varying. I think he was conceiving of how the area was changing as the animation was progressing. And I think when we talk about time, if we go back to what Thompson talked about with conceptual time versus perceived time. And I think that in order, so to answer your question, I think that in order for time to be a variable that students would actually attend to, that we could then claim covariations happening, is for students to conceive of time as conceptual. And by that I mean they could control the time. So they could imagine time speeding up or slowing down. And when I see work from Tomas, I don't get evidence from him that he was thinking about time as a variable that he could speed up or slow down. I think about him envisioning of something as it's what's happening. And so in terms of thinking about time, something that you'll notice is that in this particular case, the quantity represented on the horizontal axis, as the animation moved, the height changed at a constant, the height was not varying in the speed at which it changed for the animation, although students could control that if they wanted to. I think that when we're representing quantities that are on these different axes, there's a lot to be said about if we want to move students to covariation, that problematizing this quantity here being something that students could control, a way to do that is to create a situation where that quantity isn't changing at a constant rate with respect to time.
Yeah, maybe related to that, in your case, one of the variables, the height or the length, is proportional to time. So that's kind of a special situation. So there,
yes,
it kind of makes it more, to me it seems maybe more likely that they really could be thinking of time as the independent variable.
Yes.
And if you'd had two things that were both varying not proportionally with respect to time, that might be different. And then another related thought is, you've really presented a function parametrically as
yes.
opposed to kind of input-output or
yes.
A relation, a particular type of relation.
Yes, and so to take both of your points, yes, we've actually done some work with quantities with different measure spaces, because I think there's not just something about the quantity, but also about the measure space within the quantity, and that working with students coordinating quantities from two different measure spaces, we've done some work in terms of thinking about just the quantities from the same measure spaces, and really think that makes a difference. And in terms of thinking about time, one of the thoughts in representing time on the horizontal axis was that I was concerned that students would think about the height on the graph and the height of the triangle as being the same thing. So the picture, like I actually saw some students, like they drew triangles on the graph, so they kind of connected the height, and I wanted to be able to have that orientation be different. And so, Sibylla, to answer the other part, yes, when the variable represented on the x-axis changes at a non-constant rate with respect to time, we were able to shift a student's reasoning from variational to covariational in a different task. So that's kind of like that would be part two. It's just the analysis isn't quite, we don't have quite, but that's like, it was pretty exciting for us and the student who's like, oh my gosh, I totally wasn't thinking about two things. So that's kind of where it's going. But we're looking at, where do we need to start, that if we want students to be there, where do we need to start, and what are the pieces we need to build up with it. But then when you also talk about function, it's, in the work with function, we've been really trying to work with this perspective where we're not taking these things that we call function and rate for granted. That, we give these things called function and rate names to represent particular relationships or those kinds of things, but thinking how students might actually come to develop these ideas and how we might foster it through those relationships. Yes.
So it seems to me that all the key constructs that you're attending to in this talk, so students attending to the shapes, students attending to numbers, students attending to measurable attributes, students attending to variation, are sort of orthogonal to thinking about whether or not the quantities are variable or continuous or discrete. And you're presenting this whole talk and making claims, based on sort of one class of situations where the variables are continuous. How do you think that affects the results that you're getting?
And so one of the things that we did, so in some other work that I've done, I've presented students with situations that, from my perspective, involved a discrete quantity. And I've also, in this case, presented students with things that, from my perspective, involved a continuous quantity. And what I found was that the nature of the quantity from the perspective of the person working on the task mattered a lot more than what the particular, what I thought that quantity was. And I liken this back to I left out images of change from the beginning of the talk because I thought it might take a little while in terms of kind of framing that. But I think a lot about students' images of change. And when I defined variational reasoning, I talked about students conceiving of change as being in the process of changing, as opposed to paying attention to how much had changed at particular times. And so when I think about this in terms of designing tasks, whether they be quantities that are continuous or discrete, I design tasks that are in the process, that are to provide students opportunities to think about things in the process of changing. Some work that I did with high school students on a task that was pretty similar to one of the AP calculus tasks that involved like temperature of a city, and asked students to think, temperature versus days. So we had a discrete quantity in terms of being related, and I found that students engaged in reasoning about that didn't differ from the ways in which students reasoned about the bottle problem, where the volume and height were both continuous quantities. So the way that I think about it is that I think about the images that students have for change matters more than what we would talk about the quantity as being either discrete or continuous, so that potentially both could afford it, but the images of change are what matters on the part of the student.
I guess what I'm still wondering about is when you sort of point to constraints in students' reasoning in these examples, to what extent are those constraints struggles to deal with smoothness? Is it about variation, or is it about smoothness? I don't really have a sense of that from these data.
And so when you're saying that it being about variation versus about smoothness, one of the things that I can answer is yes, in terms of it's about variation through which students perceive that variation as being smooth, in using that as a proxy for in the process of changing. Constraints that I think that have what I mentioned in terms of the measure spaces, I think the measure spaces of the quantities that we're relating makes a difference. That with working with this task and also tasks like the bottle problem, where we're asking students to coordinate a quantity that can be measured in one-dimensional space versus 2 or 3-dimensional spaces, that I think that adds an issue, that if we bring both down to one-dimensional, we can get a lot more interesting results from. And so I think that that's something that I would consider just in terms of a constraint.
Please join me in thanking Dr. Johnson for giving us a wonderful talk.